All right, let's see if there's how much of a difference there would be if we use the continuously compounded. If I happen to have an account that everything else is the same, but it's continuously compounded. So now we're going to make use of the A equals E to the RT formula. So the amount is still going to be the $60,000 that we're going to need to buy this fancy car. P is still going to be the $12,000 that I invested initially. R is going to be 0.02, solving for T. So it's still going to be 5 equals E to the 0.02T. And if I change that into logarithmic form, what would it be? Yeah, the natural log of 5 equals 0.02T.
Yeah, you're still waiting on.
So what would T be in that case?
80.4. Oh, wow.
So it reduced the amount of time a little bit, right? She'll have to wait a few less months if I found a continuously compounded account versus a compounded interest account. But I mean, if you've waited 100 years, then, you know, what's a few more months anyway? I think that what would have a bigger impact would be the interest rate, as opposed to the number of times that it's compounded. The interest rate, if you have a larger interest rate, you're adding more each time. So, you know, it obviously doesn't make that much of a difference the number of times it's compounded. What makes the larger difference is the actual interest rate. Okay? But odds are from this scenario, it looks like it's saying that you hang up the dream of getting a fancy car. Right? That's the life she chose. She chose a poor school teacher. But she made really bad decisions. She chose to become a poor school teacher and then married a poor school teacher. Bad decision. Hey, but at least we're happy. All right, look at your, and my car doesn't have the automatic locks. She has to sit out in the rain until I can get inside.
That's what I'm saying.
Right. All right, go to your study guide. Let's work a couple of these problems together. Why don't you try number 9 on your study guide? You try number 9. So in 9, you have $4,750 to invest in an account that has an annual interest rate of 3.75%. It's compounded semi-annually, and that right there tells you which of the two formulas to use. It's compounded semi-annually. Use this formula. And it says how long will it take for the investment to earn $3,000 in interest. So we've got to go through and identify each of those, what each of those different amounts represent. It's $4,750 is invested in the account. So what does that $4,750 represent? It's the principal. Invested in an account with an annual interest rate of 3.75%. So there's R. We got to change it to its decimal form. So 0.0375. It's compounded semi-annually, so what does that tell you? N is 2, right? N is the number of times compounded per year. So N would be 2. If it were compounded quarterly, what would that mean? N would be 4, right? Monthly, N would be 12, and daily 365 or whatever it might be. How long will it take? So we're trying to find T for the amount in the account to earn an investment of $3,000 in interest. Okay, so now we want the amount at the end of the time period to be $77.50 because we want Now, the original amount that we put in there is still in there. That doesn't go away. We just want to put $3,000 of interest on top of that. So now we'll have a total of $7,750. We just want to know how long is it going to take for me to earn this $3,000 in interest in this particular account. So first off, let's divide over that 4,750, and what do you get in that case? 1.632. All right, and that equals, inside parentheses, we have 1 plus 0.0375 divided by 2. And what does that become? 0.19. Right, to the 2t. And then now what we've done is we've gotten it in its exponential form. So then we can convert it over to logarithmic form. So it's going to be log, and what's the base of this logarithm? Okay. What's the argument of this logarithm? And that's equal to 2t. So then we can put all this in our calculator, either using the change of base or whatever operation you use. And then we'll divide by 2, and what ends up being the time period? Okay, so 13.01, is it 010? Okay. So 13.010 years. So that really wouldn't be that long to earn $3,000 in interest. I mean, shorter than the last example. So 13 years is a long time, but yeah, it's pretty high interest rate. You know, this can also work against you too, because you know, if you borrow money, there's going to be an interest rate at which you're having to pay interest for the opportunity to borrow that money. So, and of course, the interest rate for money that you borrow is a heck of a lot higher than the interest rate for money that you invest.
Are our graduation fees interest? So I should have said something like that when I paid my deposit.
We're just asking a random question.
I don't know. I wouldn't think so.
I mean, it's a positive 50, and I mean, he said you got to pay him back anytime before February 2nd, but I swear he said the word interest in that statement.
It might be after a certain date that you would start having to pay interest. This is why when you go off to college and you walk through the student center and this man or a woman has got a table set up and they're offering you to sign up for a credit card, and they know exactly how to play on college students because they'll say, hey, if you sign up for this credit card, I'll give you a free t-shirt. And in college, that's a big deal because that's one more day that you put off laundry, So, okay, sure, I'll do that. And the problem is then you use it, and those credit cards typically come with an interest rate of something like 18 or 19%, which grows dramatically. So you got to be very careful about that. So a pizza, a $5 pizza that you pay on a credit card, and then you don't pay off that credit card for 5 or 6 months, and that $5 pizza has quickly become like a $62 Little Caesars pizza once you've paid off the interest, So you got to be real mindful about credit cards. They have a pretty substantial interest rate. All right, let's do number 10 together, and then I'll answer any other questions you have from the study guide. It says, how long would it take for an investment to double in an account that has an interest rate of 4.25% that's compounded continuously? So that last little bit, compounded continuously, tells you which formula to use. And which one would that be? The PERT formula. A equals PE to the RT.
So can you just choose any value you want?
Yeah, good. It says, how long would it take for an investment to double? Well, it doesn't really tell you what the initial investment is, nor does it tell you what the end result's going to be. So, Brenda's actually right here. You can just choose any values that you want. I mean, let's say that you initially invest $1,000. What would the amount be? $2,000. I mean, if I were to plug in $1,000 for P and then that would make $2,000 for A. What's going to happen when I divide by 1,000? I'm going to get 2, right? If I invested $5,000 initially, what's A going to be? 10,000, and when I divide by the 5,000, I get 2. So really, what ends up happening is no matter what the initial investment is, you're going to divide by it, and it's going to turn out that A would just be 2. Okay. So even if I were just to plug in 1 for P, A would be 2. But in the end, when I divide by that A amount, because it's doubled, then it turns out that 2 is going to equal E to the RT. And what's our interest rate? 0.0425. All right, rewrite this in logarithmic form.
Natural log of 2 equals 0.04.
And so we'll do in our calculator the natural log of 2 divided by 0.0425. And how long does it take for that investment to double? 16.309. And in the big scheme of things, taking 16 years for an investment to double is a really fast time for an investment to double. Now, 16 years seems like a long time, and it is, but in terms of an investment doubling in size, it's a pretty substantial and pretty quick time for that to happen. All right, what other questions do you have on your study guide? We have probably about 10 minutes or so. We're answering the questions of your study guide. They already are. I mean, because I'm efficient, right? All right, 18 is a good one. We have 7 raised to a power of 2 log base 7 of 6. And one of our lesser properties of logarithms was if you have this, what happens? Yeah, you're left with just B. Okay? And the reason for that, remember, is that logarithms and exponentials are inverses of each other, so they cancel each other out. So if the logarithm is in the exponent, then it's going to cancel itself out because logarithms and exponents are inverses of each other. Now, the only caveat to that is that this base of the logarithm and the base of the exponent have to be the same. It can't be, the log base 2 and that be an exponent of 5, because those aren't going to cancel each other out. They're not inverses of each other. Log base 2 is the inverse of 2 to some power, and they'll cancel each other in that case. We don't have the exact correct setup here because we have a 2 in front of that logarithm. And over here you'll see that the setup is just a logarithm. But what can I do with that 2? Yeah, I can make it the exponent of 6. And now, because these bases are the same, and that logarithm is up in the exponent, then it's an inverse, so it's going to cancel out. And what are you going to be left with?
36.
Yeah, 36. 6 squared, which is 36. Yeah. No, I mean, if I gave you that, you couldn't do anything with it. So I wouldn't do that. Yeah, or it would just, like if I gave you 3 log base 2 of 7, you just leave it like that. Because there's nothing you can do to evaluate that. Any other questions do you have?
Number 17.
Teachers, please pardon the interruption.
Natural log of
Please do not send students to the restroom in the annex until further notice. Teachers, please do not send students to the restroom in the annex until further notice.
All right, 26, we have the natural log of x plus 3 over the cubic root of x squared plus 4, all of that squared. And you're to rewrite this in the form of a logarithm with no product, quotient, or power. We want it in this expanded form. Well, the very first thing is the squared. We've got to get rid of that before we can do anything inside the parentheses. So where does that 2 go?
In front of the,
Yeah. So it will be 2 natural log of this quotient. Now we have the logarithm of the quotient, and we can separate that out by subtraction. So we'll have 2 natural log of the numerator minus 2 natural log of the denominator. So that 2 has to follow each of those logarithms. Is there anything we can do with the natural log of x plus 3? No, because x plus 3 doesn't have a product, quotient, or a power. So we're done with that. What about the cubic root of x squared minus 4? Yeah, the cubic root could be rewritten as an exponent of a third. And then what can I do with that 1/3? Move it to the front. So it's going to be 2 natural log of x plus 3 minus 2/3 natural log of x squared minus 4. What about x squared minus 4? It's the difference of 2 perfect squares, which means it's factorable. And then once it's factored, it's a product. So we're going to have 2 natural log of x plus 3 minus 2/3 times the natural log of x minus 2 plus the natural log of x plus 2. And I could distribute that negative 2/3 in if I wanted to.
Wait, so if you didn't write it with parentheses, would the negative 2/3 go on both?
Yes, go on each of those natural logs.
Oh, we can't.
You can leave it with parentheses. Yeah, the only reason you would need to know that is if it were like a multiple choice question. You'd have to try and make your answer back. All right, any other questions on study guide? 37. At 37, we have log base 2 of x plus 2 minus log base 2 of x plus log base 2 of 2x minus 1. And that's all equal to 3. You have multiple logarithms in this equation, but we've got to consolidate them down to a single logarithm. And the first 2 logs with the same base are joined by a minus sign. So that would become log base 2 of x plus 2 over x. Then you have 2 logarithms with the same base joined by a plus sign. So we're going to multiply. And where's that 2x minus 1 going to land? So we're going to have log base 2 of x plus 2 times 2x minus 1 all over x. And that's equal to 3. And now we've isolated the logarithm. So we can rewrite this in exponential form. And what's it going to look like in exponential form? 2 cubed, which is 8, equals x plus 2 times 2x minus 1 all over x. And then this becomes an algebra problem. I'm going to cross multiply. So it's going to be 8x equals x plus 2 times 2x minus 1. That's really a quadratic equation that needs to be set equal to 0 and factored. So I'm first going to have to FOIL that out. Now I'm going to subtract the 8x over. And I'm going to hope it's factorable, which it's not. So then what do I have to do? Quadratic formula. It's going to be negative b plus or minus the square root of b squared minus 4ac all over 2a. And I'll get my values from that. And you need to check both the positive and the negative to see if either of them are extraneous. I suspect that the negative one, I suspect when you do 5 minus the square root divided by 4, turns out to be an extraneous solution. About 30 minutes. Set equal to 0, so if there's any factoring that we can do, that would help. And is there any factoring? Yeah, the GCF. What's the GCF? 10 to the x. Which leaves me with 4x squared minus 11x plus 6. And that's factorable. That's 4x minus 3 and x minus 2. So what are two solutions that you can tell right off the bat? 3/4 and 2. The other solution would be if 10 to the x equals 0, but that doesn't happen, so we can ignore that. So our only solutions are 3/4 and 2. All right, tomorrow is your test. And make sure you've gone over this, but also go over your class starters and your homeworks. Remember that tomorrow, pay attention to this, tomorrow you must bring your textbook. If you forget your textbook tomorrow, you will not be allowed to take the test. That means you will have to come Thursday with your textbook to take the test. Okay? I can check, I can check and see who else turned it in, but bring your textbook. Okay? Has anybody else turned their textbook in already? So bring your textbook. Make sure you have your binders, your parent function flip books. Make sure if you borrowed a calculator from the school that you have that tomorrow to turn in as well.